A review on internal combustion engine fins. Abstract extended surfaces has its major significance in heat transfer and thermal management in internal combustion engine. They plays a major role in performance of combustion engines. In this paper, heat transfer effectiveness of fins were studied also with literature survey to identify the previous works that have been performed by mathematical, analytical, and numerical methods with optimizing profiles, materials and process parameters. This survey paper segmented and clustered the detail. Description of internal combustion engine fins. This paper reviews the recent researches that were performed in heat sinks by considering various parameters and methods. Keywords: convection, fins, heat dissipation, thermal analysis, air-cooled engines, water-cooled engines, heat transfer coefficient. Introduction. Internal combustion engines are part of economic development in world economy in present era. The goods that are imported by means of heavy vehicles like trucks and buses are working in internal combustion engine. Although passenger vehicles and civil construction heavy vehicles also works in internal combustion engines, these engines generates high amount of heat during working. This heat is dissipated by means of fins with air-cooled, oil-cooled, and water-cooled engine systems. The cooling of engines thoroughly depends upon the fins. It is classified as air-cooled engines, oil-cooled engines, water-cooled engines. Air-cooled engines. These type of engines are used in both spark ignition and compression ignition engines. It consists of fin in combustion cylinder. The air direct interacts with cylinder, the cylinder gets cooled by means of fins. Oil and water-cooled engines. Oil-cooled and water-cooled engine with fin configuration are terms employed by manufacturers to identify the slight difference between the cooling systems. Oil cooling. Technically, an oil-cooled engine is an air-cooled with oil cooling assistance. The bulk of the thermal effectiveness transfer is from the fins on the engine block. Air-cooled engines are predominantly fuel-efficient, economical, and require lesser engine area as compared liquid-cooled engines. The upkeep costs of liquid-cooled ones are above air-cooled engines. 28. 2. Cooling fins. 1. Fins are the extruded surfaces created to extend heat transfer rate for a definite surface temperature, or to decrease surface temperature for a defined heat transfer rate. 27. 2. Heat transfer by convection between two surfaces, and therefore the fluid around the surface are often increased by fabricating to the surface called fins. 27. 3. The conduction of heat through solids, walls, or boundaries has got to be dissipated to the environment to maintain the system during a steady state condition. In many engineering applications, large quantities of thermal exchange is needed to be dissipated from tiny areas. 27. 4. The fins increase the effective surface area of any model, thereby increasing energy transfer by convection. Rectangular fin and triangular fins are straight fins. Triangular fins are attractive, since for an equivalent heat transfer it needs much low volume than rectangular fins. Hence the fins have practical importance because it gives maximum heat flow per unit mass with easy manufacture. 27. 3. Structure of fin. The structure of fin supports in effectiveness of heat dissipation. Many researchers have proposed different shape of fins and predicted the heat transfer effectiveness in different heat flux, as well as parametric evaluation have been performed by varying fin thickness, fin spacing and length of fin. The different type of fin structures are rectangular fin, offset strip fin, triangular fin, perforated fin, wavy fin, louvered fin. Many of researchers investigated variable outcomes in analysis of fin by performing numerical simulation. Mathematically and experimentally, the survey had been done on different types of fin shape to predict behavior of heat dissipation and temperature distribution. 1. Further material of fin is changed to predict behavior of heat flux and temperature distribution, including different shapes of fin. 2. The effect of convection condition with conduction on fins were analyzed for improvement in higher heat dissipation. 3. Natural convection analysis had been performed in fins using software simulation with finite element method for determination of high thermal effect and compared outcome results obtained by variable parameters. 4. Proposed design of fin considering transient fuel as a working fluid with analyzing distribution of heat with optimization in design of fin. 5. The potency of different fins by optimizing their form were reviewed for prediction of thermal efficiency. The review is also done for prediction the thermal effects on fins by finite volume method and finite element method. 6. Effective cooling performance is analyzed by varying fin thickness, fin spacing. The analysis is performed in ANSYS software by applying parametric evaluation and determined optimum dimensions for effective cooling performance. 7. Combination of circular and strapped fin with magnesium and aluminum 6061 were used to enhance the heat transfer rate using finite element method. 8. Further, the survey has been performed in 4-stroke spark ignition engines. The different configurations with materials were predicted and study was done on variable profile of cylinder block that were used in different vehicles. 9. Thermal performance of fins that were performed using finite element method in different materials were evaluated with highly thermal conductive materials 10. P. Senthil Kumar et al. 21. In this study, design of circular fin has been done by finite element method. The investigation is performed by comparing the different profiles of fin with determination of thermal stress. Also the parameters were compared in form of temperature distribution, heat flux as well as structure of fin. Yang Su et al. 22. Investigated thermal performance by parametric evaluation with different configuration of fin including impingent flow. The final observation is the optimum ratio of distance between fin and spacing ratio develops maximum heat transfer characteristic in inclusion if impingent flow. Su Minhoi et al. 23. The study represents a fractal shaped inserts in plate fin heat sink to enhance convective heat transfer. Increase in heat transfer is analyzed by varying thickness of fractal. The results were compared by evaluating Reynolds number with each optimized design of plate fin heat sink. This study also proposed that fractal inserts with unity enhances overall thermal performance of plate fin heat sink. Ngoktan Tran et al. 24, presented the configuration of louvered fins and improved 19.54% of thermal performance using forced convection. The velocity ranges that were considered is between 1m/s to 6m/s with louvered angle between 27 degree to 40.5 degree. The results are compared together and heat dissipation is improved. Laley et al. 25, the pin fins including the inner cavity increases the circular flow and make it move beneath, in order that the Nusselt number within the area below the pin fins is enhanced. Meanwhile, local convective heat transfer coefficient and therefore the area of thermal exchange have both increased to enhance the convective heat transfer effect. Adil Tariq et al. 26, the experimental data validates the conjugate model of heat sink using finite volume method. The results from the FVM model show that the heat transfer coefficient is higher in the plain fins without slots and perforations. Also need of pumping power is compared to be less in comparison of base model. Conclusion. After surveying several literatures of engine fin, the following conclusions were withdrawn. 1. More improvements could be made by considering the materials like graphene and aluminum foam. 2. Fins with different profiles of perforations should be used and would be analyzed for more improvement in heat transfer. 3. Pin fins with slanted edge would be employed in heat sink, which would increase the heat transfer rate because slanted edge have capability to converge the flow. Due to this, effective cooling would be done. 4. It can be concluded that even performing the several attempts have been made to optimize several parameters related to fin for heat transfer augmentation, but still there is a huge scope for fin design modification and optimization.